So in this tutorial, we're going to solve one of the chapter 8 questions and utilize the Rayleigh Ritz method to find the approximate solution for the displacement function. We're actually going to find the exact solution first and then find the approximate solution and compare both. So for this problem, we have a bar with a length of 2 meters aligned with the coordinate axis x1, and the width of the bar is equal to 250 and the height varies linearly. The height is equal to 500 millimeter when x1 is 0 and 250 meter when x1 is equal to 2 meters. The bar has a constant force of value 200 Newton applied at the end x1 is equal to 2 meters. The bar is fixed at the end x1 equals 0, and we're interested in finding the displacement of the bar by directly solving the differential equation of equilibrium and then by using the Rayleigh Ritz method, assuming a polynomial of the degrees 0, 1, 2, and 3. And we need to assume that the bar is linear elastic. Young's modulus is equal to 100,000 Pascal, and assuming that small strains and ignoring the effect of Poisson's ratio. So first, to find the exact solution, we need to solve the differential equation of equilibrium. First, I'm going to clear everything. U1, U2, U3, U4, stress, strain. These are the variables that I'm going to use. The area is equal to 0.25, so I'm going to I'm not going to use decimals so that Mathematica gives me exact numbers. So that's the width multiplied by the height, and as we if you look at the online lecture, the height is equal to 0.5 minus 25 over 200 multiplied by x. So this is the height of the beam. So we need to clear x as well. Maybe A. So this is the height and this is the area. And let's find dA by dx. Let's call it dA dx, which is equal to dA with respect to x. Alright, so this is dA by dx. Young's modulus is equal to 200. So 100. 1, 2, 3. I'm going to use Newton and meter, so Pascal. And the length of the beam is equal to 2 meters. And the applied force is equal to 200 Newton. So the differential equation of equilibrium, as if you look at the lecture, is E multiplied by the second derivative of the displacement, and let's make everything function of x, multiplied by the area, plus Young's modulus multiplied by the first derivative of u with respect to x, multiplied by dA dx, equal to 0. And the boundary condition is u when x is equal to 0 is equal to 0. Sorry, u when x is equal to 0 is equal to 0, and the boundary condition for the stress is that u prime of L is equal to, or basically the stress is equal to P, and so the stress is equal to E multiplied by the strain. This is equal to P divided by the area, and that's only at the area at the end, so this is PA when x is equal to 2 meters. Solve for u in terms of x. Shift enter, and we get 8 over 125 ln 4 minus x. So this is the exact solution. I'm going to just save it. So I'm going to call it u exact. And so this u exact is equal to u of x when I utilize this variable inside the list of solutions s. Shift enter, and this is u exact. And I can find the stress inside the bar. The stress 1 1 is equal to Young's modulus multiplied by the strain 1 1. So let's call it, this is stress 1 1, strain 1 1. Stress 1 1 is equal to E multiplied by the strain 1 1, and the strain 1 1 is equal to d u exact with respect to x. So this is the strain and this is the stress. So this procedure, we found the exact solution. Now to find an approximate solution, for the approximate solution, first we need to assume a displacement function. So I'm going to assume u1 to be equal to a0. And as you show, if you look at the lecture, the online lecture, we cannot assume this because the boundary condition, the essential boundary condition is that the displacement is equal to 0 when x is 0, which will give me this a0 to be equal to 0. So I can't use this. The only function, or the first function I can use, is a1 multiplied by x. So this is the approximate solution. 1 degree polynomial after satisfying the essential boundary conditions. So the question is, what is A1? To find A1, I need to find the potential energy of the system. The potential energy of the system is equal to integrate the internal energy. The internal energy is equal to 1 over 2 multiplied by E multiplied by the area multiplied by multiplied by d u1 with respect to x squared, which is partial u by partial x squared, integrated over x from 0 to L. So this is the internal energy of the beam, minus the work done by the forces, the P, the only external force is the force P, multiplied by the displacement. And this displacement is evaluated when x is equal to L. And so the potential energy of the system is equal to the internal energy of the beam minus the force multiplied by the displacement. So this is force multiplied by the displacement at this point, and the displacement of this point is equal to A1 multiplied by L, which is U1 when x is equal to L. Shift enter, and here's the potential energy of the system. You can see the potential energy is function of a variable called A1. And the question is, what is A1? And we're going to utilize the fact that potential energy has to be minimum at equilibrium. So I'm going to differentiate. I'm going to call this equation 1. Differentiate the potential energy with respect to this A1 constant. And I get this equation. I would like to find the minimum potential energy by minimizing A1. So solve. Equation 1 is equal to 0. Find A1. And A1 is equal to 8 over 37. So U1, U1, this is the approximate solution, is equal to U1. Let's just call this A. When I utilize A. So now replace A1 with 8 over 375. Shift enter. And you get 86 over 375. Let's compare the two solutions. Let's plot U1 and U exact when x changes from 0 to L. Shift enter. You can see that this is the log function, the exact solution, and the blue line is the approximation if I use a linear function to approximate this logarithmic function. Now let's try a better approximation. So I'm going to use a better approximation. I'm going to copy everything and paste, and instead of approximate solution first degree, second degree polynomial. So a1x plus a2 multiplied by x squared. And now I have two unknowns I would like to find, a2 and a1. The potential energy will not change. Potential energy is this integral. It will not change. Now I'm going to have two equations. One is the partial potential energy with respect to a1, and equation 2 is partial potential energy with respect to a2. And I just want to show you those two equations. Shift enter. This is the first equation, and this is the second equation. Two equations. I want to make both equal to 0 so that I find a1 and a2. Sorry, this should be u2. So solve. Equation 1 is equal to 0. Equation 2 is equal to 0. Solve for a1, solve for a2. And u2 is equal to u2 after I realize that solution. And let's add u2, u1, and u exact in the plot. Shift enter. And you can find actually that u2 actually the potential energy will actually change because we're differentiating. The potential energy's function is half E multiplied by A multiplied by the first derivative of U2, because now we're calling, let's call it potential energy 2. The first one is potential energy 1. Potential energy 2 is we're taking the second degree polynomial, what we call U2, and this is what we're using for the potential energy, and this is also U2. So equation 1 is partial potential energy 2 with respect to A1, partial potential energy 2 with respect to A2. And similarly here, I'm just going to differentiate potential energy 1 and potential energy 2. Alright, shift enter, and you get, this is A1, this is A2, and this is the solution. And you can see that the exact solution and the approximate solution with or second degree polynomial are very close to each other. Now let's look at the stress. At the top here, I'm going to find the stress 1. Stress 1 is equal to EE multiplied by du1 with respect to x, which is the stress 1 is equal to E multiplied by the strain. And the stress 2 is equal to E Young's modulus multiplied by the strain, which is du2 with respect to x. And let's plot the exact stress, or stress 2, stress 1, and the exact stress, which we called stress 1, 1. Shift enter, and you can see this is the exact stress, this curved function. The first polynomial, when I use the displacement to be constant, to be a linear, the stress is constant because the stress is equal to E multiplied by the first derivative of the displacement. So I get a constant function, and then I get a linear function. So you can see the stress is really not close to the strain, to the exact, so the approximate. The approximation for the stress is not very good. It's not as good as the displacement. When I use an approximation for the displacement, it's almost as good as the exact, but for the stress, it's really far. I actually need to do it a third time to get a good approximation for the stress. So I'm going to copy this and paste, and third degree polynomial, so I'm going to call this u3. So this is a3 multiplied by x bar 3. The potential energy 3 is equal to this, the first derivative of u3 minus the work done by the force, which is p multiplied by u3. The equation 1 is partial potential energy with respect to a1. a2, I have to add another equation, which is partial 3 with respect to a3. And now I have three equations. Equation 3, a1, a2, and a3. u3 is equal to u3, and the stress 3 is equal to du3 respect to x. So let's add stress 3 here as well. Shift enter, and you'll find that the third stress will be closer. That green, that new one, the green one, is closer to the exact. So it took us, for the displacement, the first degree was far, the first degree, which is the linear function, was far. The second degree was a good approximation. For the stress, the first degree was far, and the second, when I used the second degree for the displacement, the stress was far, but when I used the third degree for the displacement, the stress was closer to the exact solution. So we're going to solve another, in the next tutorial, we're going to solve another example for beams under lateral loading, and in that case, all what will happen is that the expression for the potential energy will change. This expression for the potential energy, which is equal to half the stress multiplied by the strain squared, or half the stress is equal to E multiplied by the strain, so half E multiplied by the strain squared. So this applies for beams under axial loading. In the next tutorial, we're going to use a different expression for the beams under lateral loading. One thing to note is that it's better to apply a plot legend or provide a plot legend for the plot and label the axes. Otherwise, I don't really know what I'm looking at right now. So for your assignment, you have to label everything. So I'm going to show you just for this how to label this plot. So to label this plot, so let's just label the last one. So axis label, or axes label. The axes, the label of the axes, the horizontal axis is x in meters, and the vertical axis is stress in Newton per meter squared. Shift enter, and indeed I have to put two curly brackets. So curly brackets, the axes label, the first and the second. So shift enter, and you get, this is x in meters and this is stress in Newton per meter squared. Now I also need to supply a legend. So to supply a legend, I'm going to, I have to write needs plot legends, and then I can provide a plot legend. The first is stress 3, the second is stress 2, stress 1, and exact stress. perhaps the plot legend has to be at the end. I'm just going to copy plot legend. Okay, so there it is. This is stress when I used the green is the exact. This color is when I used the first approximation for the displacement. This when I used the second approximation for the displacement, and the blue is when I used the third approximation for the displacement.